All right, so far we mentioned that a block cipher takes input as B bits and provides a B bit output, right? So now two questions arises when we are using block ciphers. Since a block cipher works on blocks, how to encrypt plain text longer than a single block, right? This is the first question. And the second question is how to encrypt a plain text whose length is not the multiple of the block size. This means that what if the block size is 64 bits and I just want to encrypt 7 bits, right? What do you do? I mean, you can fill the rest with zeros, but this would cause some problems. So let me start with the motivation for the first question. So assume that I have more than one blocks to encrypt. So I have n plus 1 plain text blocks here. I have a single block cipher with a single secret key. So the easiest thing you can do is to independently encrypt all of the blocks with the same encryption algorithm, with the same secret key, and obtain ciphertext blocks and concatenate them at the end. Okay, and also this is the worst thing you can do. ECB maps same plain text blocks to same ciphertext blocks. This means that if P0 equals to P2, then C0 equals to C2. Attacker can capture information using the redundancy of the plaintext. Recall that the plaintext has redundancies. So here's an example. Assume that you have a bitmap file. So this is a rectangle like this. And if you encrypt this using AES in the ECB mode, this is the output. As you can see, we can still even read the name auto. We can see understand what the picture is all about. So you are using a worldwide standard encryption algorithm, but it doesn't provide you any security. But of course here, for the people who are going to ask the question, so since this is a file, at the beginning of the file, you use some headers like that. This is a BMP file, you write the resolution and so on. So if you encrypted it and then double click it, actually your software will say that it is not compatible. Here I'm making a small modification at the beginning of the encrypted file saying that this is a bitmap file. And just by looking at the size of the image, you can actually guess what the resolution is. But the thing is that you shouldn't see any patterns at all, because you can understand that there are many white pixels here. So FE pixels becomes blocks, right? So those blocks are mapped to the same encrypted block. This is why we see patterns like this. Okay. So BMP files are good examples why ECB fails in practice. This problem is not limited to BMP files. You can treat an encrypted file as if it is an image file and look at the pattern of the pixels to discover the type of the original file. For instance, executable files can be identified from the ciphertext because operations like memory accesses provide a distinct pattern in the image file. ECB mode can be used for implementation verification or benchmarking, but the warning is that ECB mode should never be used for cryptographic purposes. Again, this is important and not many people know this. So the solution, I will show many solutions, but the idea is to somehow, the easiest solution would be to linking plain text blocks to each other. For instance, in the cipher block chaining mode, you encrypt one block, but take the ciphertext and XOR it with the next one. This way, even P0 and P1 are identical, C0 and C1 will be different, right? Because now, because of this XOR, you are going to encrypt something else. Let's move on to the motivation for the second question. So question was, what if we are going to encrypt something which is not a multiple of the block size? So if a plaintext is not a multiple of the block size B, we can fill the remaining bits with zeros. So this is the first thing that comes into mind. But the question is that the last bits of 0 of the last block may belong to the plaintext, or some of them may be from the padding, right? So the person who is decrypting it will have an ambiguity and wouldn't understand. For instance, consider the 64-bit block like this. As you can see, the last 8 bits, the last byte is all 0. So question is it from the padding or is it from the plaintext? If you know the payload size, the plaintext size, then you cannot distinguish. But if your protocol also sends the size of the plaintext, then you wouldn't have this kind of ambiguity. You can use this technique by filling all with zeros or something else. So to remove the ambiguity about the plaintext that are not divisible by B, a structured set of bits can be concatenated to the end of the plaintext. This operation is called padding. Inappropriate padding schemes can be dangerous. There are many examples in the past. The best padding scheme is to append a single 1 bit to the end of the message and then append as many 0 bits as required. This way, this pattern, when somebody decrypts it, will remove all of the last zeros and the first one. Then, this way you get the plaintext back. So for a block size of 32 bits, here's an example. So there's a single byte missing here. So we fill it with 80 because a single 1 and 7 zeros turns into this representation. But the question is, if what the message is already of block size and it ends like this, I cannot send this because when I send it, again, the person will try to remove the padding, right? So in order to avoid ambiguity, in this case, we always apply the padding anyway. So we create a new block with ones and zeros. But this causes a message expansion because you wanted to send one block, now you are sending 2 blocks. This is also important in full disk encryption because your disk size is limited, right? If your padding causes a message expansion, then it wouldn't fit in this hard drive. So this way you need a few tricks. So the famous method is ciphertext stealing. Because of this stealing word, people think that this is somewhat of cryptanalysis. Here just I'm, avoiding padding just by switching the places of the last 2 blocks, okay? It's a general method that allows encrypting messages that are not a multiple of B, uses the last 2 message blocks, hence does not work on shorter messages, so you cannot encrypt 1 block in this case. Does not use padding, does not cause message expansion. So the picture is for ECB mode. For instance, assume that this is your last 2 blocks, and your last block is shorter than the block size, so there's empty place here. So this is m bits, let's say. So what you do is as follows. Encrypt the previous block, obtain the ciphertext. Then by looking at the empty bits here, just divide this as tail and heads, okay? Take this tail and fill this remaining part. Then encrypt it and put it as not as the last block, but the previous one. And this head, which is already encrypted here, goes here. So as you can see, we don't have any message expansion at all. Right? You can use this kind of tricks, and they're actually used. So in all of these mode of operations, we use some words like initialization vector. This is an input to a cryptographic primitive like block ciphers, hash functions, message authentication codes, stream ciphers. And nonces are arbitrary numbers that may only be used once. This is very important. Sometimes these are used interchangeably. So in some scenarios, if you are using IV as a nonce, then IV should also be used only once. For instance, when we are using hash functions, for instance, SHA-2, IV is fixed and you use the same IV all the time. So using the IV, same IV there doesn't cause a problem. But we are using the IV to initialize stream cipher. And using the same IV would result in the same key stream. So their IV reuse is a problem. So this is why I prefer to use nonce in those scenarios, because nonce has to be used only once. Again, they have to be randomly generated, right? So again, randomness plays an important role. So NIST has a document in the 2001 version of this document. We have 5 modes like this, and the 6th one added as an appendix in this document, okay, in 2000. This because this is an IEEE standard for full disk encryption, so NIST also added it. But so you can say that there are 6 modes, but the first one is electronic codebook. Again, it appears in NIST document, so people think that this is secure, but NIST is just to show how it works. So you should avoid ECB all the time. So the question arises then, which mode of operation should I choose? But the answer depends on the security and performance, okay? So let's recall electronic codebook. You divide plaintext into blocks, encrypt them independently. The person who wants to decrypt obtains the ciphertext and decrypts them with the same secret key. As you can see, the encryption and decryption are used in different colors because in some of mode of operations, you will see that both the decrypting and encrypting person are going to use the encryption function, not the decryption function. This is important just to show, because in some versions we are going to turn block ciphers into stream ciphers. Okay. So this is the electronic codebook. Again, we said that you shouldn't use it. It has a lot of advantages, like parallelizability, because if you want to encrypt PN, you don't need to wait for the other blocks to be encrypted, right? You can simply do it. So if you have N+1 core, you can encrypt them at a single trial, all of them. So it's a good thing. Random access, a block can be decrypted without waiting the decryption of other blocks. Error propagation is limited to a block. This means that if a single bit of a block is flipped due to a transmission error, it does not affect other blocks. So assume that you send C0, but there was a problem during transmission. So when the person decrypts it, P0 will be something completely different, but it wouldn't affect the results of other blocks. This is why we say error propagation is limited to a single block. Disadvantages: identical plaintext blocks are encrypted to identical ciphertext blocks. No self-synchronization, but none of these modes of operation provides self-synchronization, so it's not a problem to be discussed here, but we will see it during stream ciphers. Okay, easy solution we said was to chain these blocks. So now we are taking the ciphertext blocks to XOR with the plaintext blocks. This is called cipher block chaining, CBC. It is used a lot in practice. And the decryption is just a flipped version of this image, as you can see. To provide symmetry, actually, this is why you have an IV here. Because if you implement it in a hardware, and if you remove this part, then you have to implement this part independent and the remaining parts again. So this is why we start with an IV. So in these kinds of modes, the standardization document says which IV is fixed for that. Okay, but libraries like OpenSSL would allow you to choose any IV you want. Okay. Advantages: error propagation is limited to 2 blocks now. Fixes the security problem of ECB mode. Parallelizable decryption, but not encryption. Right? For decryption, we can decrypt this without waiting the remaining decryptions because we already have the CM-1 and XOR it here and so on. But to encrypt this, I need to know C1. In order to know C1, I need to know C0. This is why we are actually called a chaining. Okay. So disadvantages: non-parallelizable encryption, no random access. And there's also this property that if two ciphertext blocks are identical, then you can obtain this inequality, which happens due to birthday paradox when you perform this many encryptions. So if B is small, then this number is really small, right? So this is why you have to change the key and so on. So cipher feedback, as you can see, the arrow from here is now moved here. And the plaintext are not from at the top, now they're at the bottom. So as you can see, I'm encrypting IV here. So IV is fixed, but I'm choosing a secret key, so the result will not be known by anybody. I simply XOR it with the plaintext. So this is like a key stream generator. Right? I'm actually producing here random values. I simply XOR with the plaintext. I do the same thing here and here. This is why at the decryption side, person also performs encryption. So they also take the IV, they also know the secret key, they also produce the same value here as in the case of here, but the person who was encrypting was simply XORing this value with P0. Now I know C0, I XOR it and obtain P0. So as you can see now, it works like a stream cipher. Although we haven't seen what a stream cipher is, just know that this produces some random values, which is now XORed with the plaintext or the ciphertext. So I'm encrypting IV here, not the plaintext. Advantages are error propagation is limited to 2 blocks. Disadvantages: non-parallelizable, no random access, and so on. So how to overcome this? Now this looks like the same picture, but in the previous one, this line was at here. Now it is here. Okay, this is the trick. So this would allow us to have some kind of random access. So again, in the picture, you replace P0 with C0 here, and so on. Okay. So in this output feedback, OFB, no error propagation. Erroneous bits in the ciphertext only affect the corresponding in the plaintext bits, not in the whole block, but only at the bits. Encryption does not depend on previous ciphertext. This is important because here, for instance, you haven't received the plain text yet, for let's say, you can start with the IV and produce all of these values here. And once you receive the plain text, you can simply XOR this key stream and obtain the ciphertext. This is the advantage. But let's move on to our favorite, and also this is used in in iPhones or anything that uses full disk encryption most of the time. Of course, in Gallo counter mode, which we'll see in a minute, but this is just a similar idea. So counter mode is simple. You have a counter and you encrypt it. But the thing is that counters should be different for each encryption. To avoid this, for instance, in AES, what you do is as follows. Since the block size is 128 bits, we randomly generate a nonce for 64 bits. Then for the remaining 64 bits, we choose a counter. And that counter can be all zeros. Okay? So you encrypt that and then XOR it with the plain text. Then you increment the counter by 1, keeping the nonce same. Okay? So this way, you perform this operation in parallel. Of course, incrementing counter is just simply adding 1, but you can choose different methods if you want. You just need to update the counter, but everybody should be doing the same. And the person who's going to decrypt does the same stuff. Nonce is not secret, of course. For that communication, you say that this is the nonce, and you use that nonce with the counter. So these are not secret. But then the secret thing is the secret key. You obtain this value and XOR it with the ciphertext block and obtain the plain text block. So here you might think that, okay, if my iPhone uses this kind of encryption, then what is the nonce and where the counter is kept, right? Since it is going to be different for every encryption, storing all of these values for every file would be a difficult job, right? But what iPhone or similar mobile phones or similar methods do is that when you take a picture, since you are going to write that photo on the hard drive, you have to write it on the part of a hard disk, right? So that hard disk block number will be your nonce value or the counter. Since you cannot write to the same place 2 different files, you cannot use the same counter twice. So this is a nice solution. So it is parallelizable. It provides random access. Error propagation is limited to a block. Encryption does not depend on previous ciphertext. So if we go back, this is the good thing about parallelizability. You can, since there are no lines connecting these steps, because the connection is the incrementation of the counters, which is you can do without this encryption, right? So this is the good thing. So if you don't know how the counter mode works, so in Turkey, I attended to a lot of conferences and things where people say that counter mode is bad and never use it. But actually, I'm always saying that counter mode is good and you should use it. The thing is that I know that you shouldn't use the same nonce or the counter twice, okay? But initially, people didn't know it. So when CryptoLocker ransomware was famous, there was a Turkish version. So in a ransomware, most probably you click to a link in a phishing mail. So if you don't have the proper antivirus software, you receive the ransomware. It encrypts some important files on your hard drive and says that those files are now unreachable because it encrypted it and removed the secret key from the memory. Now ask you to pay some money in terms of Bitcoin so that they will connect to your computer and decrypt all of your files. The thing is that the initial Turkish version of the famous ransomware called CryptoLocker used AES in counter mode to encrypt first 2 megabytes of your files. Then ask for 2 Bitcoins to decrypt them. At that time, it was $600. So if you pay 2 Bitcoins there, probably now you lost more than $100,000. But anyway, the thing was that it used the same counter for every file encryption. Obtaining one unencrypted file allows us to decrypt every file, since XOR of the plaintext and the ciphertext provides us the key stream, which is here. So assume that all your files are encrypted, so they're in CIs here. But probably a file that's in your computer also exists somewhere. For instance, you can download it from the internet. So you obtain the P0s there, PIs. So you XOR both of these values and obtain the values here. And that is the whole thing you need to decrypt the remaining files. because you don't need to capture the secret key at all, because you have all of the values here. You get another file encrypted, you just simply XOR it with these values and obtain the plain text. So this is why some people think that counter mode is bad and weak, but actually it is not, okay? You have to know a little bit cryptography so that you shouldn't use the same nonce twice or counter twice, and know that this is a good thing. Okay, the final one is XDS. This stands for XOR Encrypt XOR based tweaked codebook mode with ciphertext stealing. Okay, a nice way of shortening it, this whole thing. AES with XDS mode is a disk encryption standard since 2007 as IEEE version this, P1619. For messages with lengths not divisible by B, the last two blocks are treated specially. Okay, so it is like a counter mode or Galois counter mode, but here, you start with a key, and the picture says it all. What you do is this looks like a counter mode of operation, but actually you apply some operations here and use it. I'm not going to go into details of this, but it is a standard. This is why I wanted to show you the picture. For more information, you can, look at the Wikipedia for that. So let's go back to our example. We said that if you use ECB, it ends up like this. But what would happen if I use the counter mode, right? The result is this, as you can see. It looks like a noise, no visible pattern at all, so it doesn't leak any information about the plain text. So this is the nice thing about mode of operations.